This example is going to use energy conservation to find out how far a block sliding down a ramp will compress a spring. But one of the key features is this is going to be a rough ramp, so we're going to have friction on the ramp, which means that when we use energy conservation, we're still going to find potential and kinetic energies at different points in our system. But now we have a case where this non-conservative work is not going to be equal to zero, where now instead this non-conservative work will have some number or something that we'll have to calculate. Here you can read the problem statement. We have a 200-gram block sitting on an incline that is 50 degrees from the horizontal. We're told that the block sits 70 centimeters from the end of a spring that has a certain spring constant, and that this spring is not compressed or stretched, so it's not attached to the block in any way. We know the coefficient of kinetic friction, and that's important because we're going to want to solve for something. For example, in here, we want to know what the distance the spring will compress before the block comes to a stop. So we're going to have sliding down this incline, this block. And so if friction is involved, we're going to need kinetic friction. And as a further wrinkle, we're told that we get the block moving down the ramp by giving it a little flick so that it has some initial speed. And that's important. So our initial speed is not zero. Instead, our initial speed is 0.2 meters per second. So there's some important details to recognize as you read through the problem statement. Go ahead and read the problem statement completely, and then go ahead and pause the video. Read the problem statement completely so you can understand it. Set up the problem and see if you can solve it. Then come back, unpause the video, and I'll show you how I solved this problem. Welcome back. You can see here the picture that I've drawn as my interpretation of this problem. I've got my incline, I've got my angle marked, I've got the surface is rough, so I've got my coefficient of kinetic friction marked. I've got my block sitting up here at the top, and the distance between the block and my spring I called L. My block has some mass, and my spring has some spring constant, and it's not stretched or compressed. But at the start, really the initial system that we want, the block is going to have some velocity. And you can see I've listed here the important details that were given in the problem statement. I also drew a second picture so that I could get everything clear in my mind. And you can see I've drawn it again where now the block is down the ramp and my spring is compressed so that, and my distance of compression I've marked as D, and this is the thing I want to know. This is what I don't know. But I do know that in order for my, to answer the question, how far will the spring compress before my block comes to a stop, then my final velocity, this velocity for this second picture, is going to have to be 0. So here you can see now I've got my pictures. I'm ready to begin to analyze and set up my equations. I need some more things though if I'm going to use energy conservation. For example, I'm going to have to define where I want the zeros of my potentials. And I'm going to define them. It may look a little strange because I have a situation where I've got on the incline, and I need some definitions for the incline because the spring points up the incline. That's the direction of the spring. And my spring potential just cares about how far my spring has compressed. So it doesn't care about X or Y. It's just going to care about this distance. However, my gravitational potential, it's going to care about the distance from which my block moves. So I'm going to have to mark and find out what this distance is. This is my delta y there. And so I'm going to have to be careful to set up my system in a purposeful manner. So let's do that now. I'm going to pick the lowest point that my block reaches. So right here where it's compressed, I'm going to pick that as where my gravitational potential energy is 0. That way, all my potentials, the distances I need for my potential energies before that are going to be positive. I'm also going to pick as the 0 position of my spring, where the spring potential energy is 0, I'm going to pick that as here on my incline. So my spring potential energy is going to be 0 there. All right. So my block starts up here a distance L above where it starts to compress the spring, and that's a distance L plus D above where it ends, which is where my gravitational potential energy is 0. And that's going to be important. So if I talk this first picture, my gravitational potential energy, I need to know what this distance is. Maybe I call that H, because my gravitational potential energy is going to be mgh. I'm a distance h above where I set my 0, but I don't have an h. What I have is I have an L plus D. So I need to mark that. I've got mg and L plus D, but it's not L plus D, it's this triangle where the angle inside, the hypotenuse is L plus D, and the angle inside is my angle, and I want this opposite side. So this is going to be a sine of theta. So it's mg, L plus D, sine of theta. And remember, m is just my 200 kilograms. G is 9.8 meters per second squared. L plus D, well, L I know. L is going to be my 70 centimeters, but D I don't know. That's the thing I'm going to want. All right, so we're already on our way, and this is a problem again we have to solve algebraically. By the way, the spring potential initially is 0 because my spring is unstretched. So this initial potential energy is just that gravitational potential energy that I just wrote the expression for. My initial kinetic energy is not 0. It's 1/2 my mass times my velocity squared, and in this case that's going to be v1 squared. Okay. Now if I have this picture 2, and I want my potential energy for picture 2, I'm down here at the point where I set my gravitational potential energy to be 0. So all of my potential energy is just in my spring, and the potential energy for my spring is 1/2 K, that's my spring constant, that's the 2 newtons per meter, times the distance my spring is compressed, that's this D distance, squared. That's my initial potential energy, or sorry, my final potential energy. My kinetic energy at this second picture is 1/2 mv squared, but v is 0, so nothing. And that's good. I want to come to a stop. So I've got my initial potential energy, my initial kinetic energy, my final potential energy, my final kinetic energy. And if there were no friction, I would be done. But this is a case where I have friction along this hill, and so I need to work out some things like what is the work done by non-conservative forces. This is no longer going to be 0, so I'm going to have to work out what that is. To answer the question of how much work is done by non-conservative forces, we need to determine what the forces on our system are. Now, we're going to need to be careful because once we determine our forces on our system, remember the force of gravity and the force of the spring, those are actually already taken care of by our conservative force. These are conservative forces, not non-conservative forces. And so these are already taken care of, the work done by them, when we defined our potential energy. So we're going to want to find out what are the forces on our spring, but we don't want to worry about the gravitational force or the spring force. Okay. Now, there's some important things to also be careful of. One thing is we should just check to see if the forces on our system, or the ones that are doing any work, end up being constant. So let's find out what are the forces on our system. If I define my box as my system, and I look at it at this point, I'm going to have only one thing touching it, that's this surface. And so I can ask myself, what forces can a surface exert? The surface can exert a normal force, and that one is of course perpendicular to the surface, and it can exert a force parallel. And since my block is sliding down the hill, my friction force is going to oppose that sliding motion, the sliding of the block's surface against the surface of the incline. So my force of friction has to point up the hill, and this is a kinetic friction force. That's it for all the things touching my block, and so now I can include the gravitational force, which points straight down. We better check just to see something, because we want to be careful of things changing. And so let's look at the block when it's compressing the spring. When it's compressing the spring, now it's touching the spring, and so we've still got the normal force, and we've got the friction force, and it's kinetic friction, and we've got our gravitational force, but we've also now got this spring force pushing us up. So we do have a change in the forces in our system from beginning to end. Thankfully, this spring force and the gravitational force are already accounted for. That was why we're using energy conservation. So as long as our force of friction and our normal force stay constant, we're okay. And even better, actually, we can look at this and we can remember that our displacement is going to be down the hill, parallel to the hill, a surface of the hill. And so since by definition the normal force is perpendicular to our hill, this normal force is not going to do any work. So the only work non-conservative we have to care about is the force of our kinetic friction. Now, what is that force? Well, let's draw our free body diagram. Here's my dot for my block. I've drawn the surface of the plane just to orient myself, or the surface of the incline, I should say. I've got my normal force, I've got my friction force pointing up, and I've got my gravitational force. And I'm going to stick with this first picture to do this. So this is my gravitational force. All right, so I want to know what my friction force is, and the only relationship I have to find it, since I don't know what the acceleration of my block is or anything like that, I know that the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. And this is why it's really important that our spring force was pointing up the incline, so that it doesn't change our normal force, and therefore doesn't change our friction force. All right, so I'm going to have to work out what the normal force is. I'm going to write down my equations, my Newton's second law equations. I've got my angle of incline. I'm going to have to work out and break things up into components. So remember, I've got now here a force of gravity perpendicular opposing my normal force. I'm going to also have a force of gravity in this parallel direction. That's going to be what is pulled me down the incline. That's what I've already calculated the work it did when I calculated potential energy. So I put those together. Now I write out my equations. Here we go. My equations end up being, if I'm going to pick a coordinate system. So let's pick up as my, let's pick down as my positive for the parallel direction, and in the direction of the normal force as positive for my perpendicular direction. And so in the perpendicular direction, I've got force normal minus perpendicular component of gravity. That's going to be mg cosine of my angle. And I don't expect any acceleration to be in this off direction. The acceleration in this perpendicular direction has to be 0 because I'm just accelerating down the hill. So this has to be equal to 0. And at this point, I'm actually done, but just for completeness, we'll write the other equation. That would be mg sine of theta minus force of friction equals mass times acceleration. That's as I'm sliding. Once I hit this this spring, then this becomes different. And this is why we want to use energy conservation, because the forces in our system are changing. We get the downward component, the parallel component of gravity, minus my friction force, minus my force of my spring, and that is all equal to the mass times my acceleration down the hill, right? So since my force is changing, I don't really want to try and use Newton's laws, and I can't use kinematic equations, right? That's the danger. Don't use kinematic equations, your constant acceleration equations, when you cannot, when your acceleration is changing. But there we go. We now know what our normal force is. I just rearrange this one and I find out that my normal force is equal to mg cosine of my angle. And so coming up here, that means my friction force is equal to the coefficient of kinetic friction times mass times gravity times the cosine of 50 degrees. All right, that got me not the work, but the force of friction. So now I need the work done. The work is just going to be the force of friction times the distance it's applied, and that's L plus D. And so let's take a moment and let me switch to a new slide. That slide was getting a bit cluttered, so I've cleaned up the clutter, and you can see it took us a bit to get what the friction force was, but now that we've got it, right, it's my coefficient of static friction, or sorry, kinetic friction, times my mass times the acceleration due to gravity, so 9.8 meters per second squared, times the cosine of 50 degrees, which, by the way, when you work it all out, this is just a number. This is just 0.25 thereabouts newtons. And that's my force of friction. So now what I want is not the force of friction, but the work done by friction. Well, that's going to be my force of friction times my displacement. And my displacement is the whole way down the incline. So my displacement is going to be L plus D. And the other thing I want, right, is the cosine of the angle between those two, between my force and my displacement. So if I look at this, my friction force was pointing up the hill. My displacement was pointing down the incline. And so the angle I have between them, this is going to be 180 degrees. So when I think about it, now I work it out. My work done by non-conservative forces is just going to be this coefficient of kinetic friction times mass times gravity times cosine of my angle times then L plus D. And cosine of 180 is going to give it a minus sign. With that, we've now worked out all the bits. We have our initial mechanical energy worked out. We have our final mechanical energy worked out, and we have the work done by non-conservative forces that move us from our initial to our final mechanical energy. So we just have to populate this equation. This is the energy conservation equation. And when we do, we get this expression. Now, this expression is pretty ugly to solve. In fact, it's going to be quadratic. You can see that if we want to find out what our d is, well, we've got a d squared in some terms and a d in some terms, and some terms that don't have a d at all. And so we're going to need to use the quadratic formula, and it's going to be something of a nightmare to try and do algebraically. So we're not going to do it algebraically, but we will massage our algebra just a little bit longer to get it into a quadratic form so you can see. If we start with the expression you saw, we can take it, and I'm just going to unpack these terms where I've got an L plus a D so that I'm just going to distribute my mg and my sine theta to both the L and the D in each of these. If I do that, I get a longer term, but something important to remember is that this is just a number, this is just a number, this is just a number. Okay, so I'm going to do a little bit more grouping, and I'm going to move everything over to this other side of the equation so that I can get it into quadratic form. And when I do, I get something that looks like this. I've got some stuff multiplying a d squared. I've got some stuff multiplying d. And then I've got all the stuff that isn't multiplying d at all. And you can see that this is then in a form of ax squared plus bx plus c equals 0. And so I can take and I can use the quadratic equation. Well, before I do that, actually, I can just plug in my numbers. Because honestly, I don't want to put this awful thing into my quadratic equation. That would be quite hairy in the algebra. But I can take my numbers and just plug them in where I need to. And so if I do that, then this reduces to something very, very simple. I just get 1 as for this coefficient multiplying d squared. This term multiplying d, I get minus 1.25, about that. And for this expression at the end, if I work it out, I get minus 0.88 with appropriate units. And that's one thing I would want to be careful of. These all have units, and I better make sure that they have the right units. But now I can just apply the quadratic formula. It's nice and easy. When I do, I'm just going to plug in for minus b, so that's minus a minus 1.25. So that's 1.25 plus or minus b squared minus 4a times c all over 2a. When I plug that into my calculator and calculate it out, of course, I get two roots, one for the plus, one for the minus. One of my roots is 1.75 meters. The other root is negative 0.5 meters. So of course I want the physical one. I can't have a negative distance being compressing my spring. And so the distance compressing my spring is just 1.75 meters. And so we've worked out now that the distance required to bring, for these conditions, to bring that block to a stop is 1.75 meters. So you can see what we've done. We used energy conservation, and we just had to work out some things. We had to work out our initial and potential and initial kinetic energies, our final potential and final kinetic energies. And then we had to do some steps with Newton's laws to work out what was the work done by non-conservative forces. And yes, there was quite a bit of math in there, and it takes a bit of time, but as you get practice, you can get faster. And it's just step by step we went through until we could build up this expression that then we could plug in our numbers and solve for our answer. So here you can see how we can treat with problems where our work done by non-conservative forces is no longer 0. Now, instead, we have some work done by non-conservative forces, and we have to account for that. One thing to be careful of, something that trips students up, is that it's always my initial mechanical energy plus the work done by non-conservative forces equals my final mechanical energy. not the other way around. Don't put this on the other side because it'll mess up our math. Always keep it on the same side with the initial initial mechanical energy. So it's my initial mechanical energy plus my final plus my work gives me my final mechanical energy. Anyway, hopefully that example gives you a pretty good idea of how to use energy conservation in different situations. And if you have any questions, come talk to me.